topic are you looking at? Water potential. It's so hard. I don't know how I'm ever going to be able to learn this all before the test. Oh, well, I found this really awesome video on YouTube. You should go check it out. Yeah.
I'm Amani.
And I'm Hannah.
And today we're going to teach you about water potential.
Now don't worry, we can assure you that by the end of this video, you'll all be experts on this. So let's get started.
So first off, water potential can best be described as the potential energy of water per unit area compared to pure water, by factors such as gravity, osmosis, and pressure. Water potential helps us to know where water is going to flow, whether it be into or out of the cell. The basic formula for water potential is represented by a symbol called psi, which looks like this, and is defined as water potential equals solute potential plus pressure potential.
So before we go any further, it's important that you become familiar with the differences between hypotonic, hypertonic, and isotonic solutions to get a better understanding of water's tendency to move into and out of the cell. Remember that water will want to move from an area of high water concentration or high water potential to an area of low water concentration or low water potential.
Cells that are hypertonic to their environment will have a higher concentration of solute inside the cell and a lower concentration of water inside the cell. In hypertonic solutions, water has a tendency to rush into the cell, causing it to swell.
Cells that are hypotonic to their environment will have a higher concentration of solute outside the cell and a higher concentration of water inside the cell. This will cause water from the inside of the cell to move to the outside of the cell. And lastly, cells that are isotonic to their environment simply have an equal concentration of solute on either side of the cell membrane, as well as an equal concentration of water on either side of the cell membrane.
Now, to solidify your understanding of water's movement in these three types of situations, or if you are still a bit unclear, here's an analogy to help you. Imagine a crowded school bus. The bus will represent the cell, the girls, represented by the pink dots inside the bus, will represent the solutes, and the boys, which are the blue dots, will represent water. Suppose the girls exit the bus, leaving more seats open, and so all the boys rush into the bus. This would mean that the bus, or cell, is hypotonic to the environment, as the boys, or water, moves inside the cell.
Now suppose all the boys exit the bus and all the girls move in. Now the cell is hypertonic to its environment because there are more girls, or a higher solute concentration, inside the cell, and a higher concentration of water, or boys, outside of the bus. In the same sense, if there is an equal amount of girls and boys inside and outside of the bus, this situation can be thought of as an isotonic solution, as the concentration of solute and water is equal on both sides of the cell membrane, or the inside and outside of the bus. Now that we have a firm understanding of hypotonic, hypertonic, and isotonic solutions, let's move into the concept of water potential.
So, water potential is going to be measured in what's called bars. And let's now keep in mind that pure water has a measure of 0 bars. When we think of a plant, water will move upward from the roots to the leaves to release into the atmosphere through a process called transpiration. So if we were to pour pure distilled water below the plant, this would create a water potential of 0 bars. But as we move upward the plant, the roots will start to have a lower water potential of about -2 bars because there is now a presence of solutes, or salts, inside the roots. As we continue to move up and the presence of solutes increase, the stem will have an even lower water potential than the roots, and the leaves will even have a lower potential than the stem.
So let's revisit that equation from before that said water potential equals solute potential plus pressure potential. So solute potential is going to lower as we increase the amount of solutes in our space. If we were to add a small amount of salt to a solution, this would then lower the value of solute potential. This is why it is important to remember the bus analogy. The drop in solute potential is because the solutes are opening up spaces for water to enter the cell. By adding in the salt, let's say for now that the solute potential is equal to -6 bars. Now let's move on to pressure potential, which is the physical pressure that water is exerting in the inner walls of the cell. So as water keeps moving in, this is going to cause the cell to push outwards. In plants, this is known as turgor pressure, which helps a plant maintain a durable structure. It's safe in plants because they have a cell wall and won't burst. In contrast to these plant cells, if water were to constantly flow into an animal cell, the cell would also push out, but it would eventually burst because animal cells do not have cell walls. Now, let's say that the pressure potential for our plant cell is +4 bars.
If we follow our lovely formula and plug in these values, that would mean that water potential is equal to our solute potential, which we said was -6 bars, plus our pressure potential, which was +4 bars. This is going to be a total of -2 bars as our overall water potential. Now, sometimes you may be asked to find more detail within the solute potential, which is given by the formula as solute potential equals -I/CRT. So I represents the ionization constant, which will either be 1 or 2, depending on if the solute ionizes or splits up into 2 molecules when added to water. If we use sugar, for example, sucrose will remain 1 molecule that, when added to water, will not break into 2 separate ones. So therefore, the I value when dealing with sucrose will be 1. C represents concentration, so simply the amount of solute that we are adding in moles per liter. The more solutes we add, the lower the solute potential will be. R represents the pressure constant, which will always be valued at 0.0831 bars. And lastly, T represents temperature, which will be converted into a unit called Kelvin. It's really easy to convert. All you have to do is add 273 to whatever the degrees is in Celsius.
Okay, so now let's try out a practice problem using the new formula to calculate the solute potential. Suppose we have 0.4 molar concentration of a sugar solution. How would we calculate the solute potential at 32 degrees Celsius? First, let's write out our formula, which is solute potential equals -ICRT. Now plug in the values. The I value would be 1, since we're talking about sucrose here. The C value would be 0.4, since this is our molar concentration. R is the constant of 0.0831, and the T value would be 305 Kelvin, since we were adding 273 plus 32 degrees Celsius. Now if we multiply these values, we will get -10.1282, making our solute potential equivalent to -10 bars.
Thanks for watching! If you like this video, give it a thumbs up.
Bye!